rather they chatting with the main thing?
Yeah, and I think that's usually
the vibe. Okay, that's what I like. Okay, good. Yeah. But just to know in case it's expected that you lecture to the last
no. We have a couple more minutes.
Yes, of course. It's morning still. Yeah, I was telling somebody like we had started something where if we wanted to do something specific, we did it on the non-zero zero. Like 59 or 1, and then 1, 11 means like whenever Greg comes at like 11:07, 10 after.
We'll give it a minute more, and then we'll get started. Okay, so it's a great pleasure to have Dave Meger here. So he made it. So we were a little bit concerned that he wasn't going to be able to make it with the weather last night. So thank you very much for making the long trip from Montreal. So it's a great pleasure to have him here. So Dave is an assistant professor in computer science at McGill University. So some of you guys may have known him for his work on Curious George, right, which won the Semantic Robot Vision Challenge back in for AAAI, right, in 2007. So now actually Dave is a very, very prolific researcher. His research sort of crosses the intersection of active perception, learning, and control. So some of you guys might have heard my story about the first time I was invited out to do, field marine robotics experiments by Dave's colleague, Greg Dudek at McGill. So this was in Barbados, which in January, which is actually a really nice time to be in Barbados. And basically Dave took me out with a bunch of graduate students. So he had his scuba gear on, the other students had their scuba gear on. They basically said, here's a snorkeling, mask and snorkel, hope you know how to snorkel type of thing. And then basically, they had the robots, they had the weights, they had the sort of air markers that they had to take out. And so here we are treading water. I'm not a particularly strong swimmer. And so so Dave is very serious looking at his GPS and sort of marking the location so they can put the floating buoy down sort of as their marker. And then he basically, hands the robot to me and go, hold this. This sort of, $1 million robot after how many years of development, right? He goes, hold on to this. We're just going to go down and we're going to set up the markers. And you said, we'll be right back. So here I am by myself holding on to this, sort of robot, trying to tread water and thinking to myself, I better not let this thing drop, right? As they were sort of going down prepping for their experiments. And so fortunately, I did not destroy anything during my visit, and I will not put you in the same position during your visit this year at this time. But I'm really happy for you to be able to make it here, and we're looking forward to your talk. Thanks,
Penny. So it's pretty cool to see someone else's perspective on the research, and we were down I can tell you that there was like 10.5 centimeters between the two markers, which is what I was focusing on, but it's interesting what these field deployments end up being like. So thanks very much for the welcome, and hello from everybody at McGill, Mila, the Mobile Robotics Lab, who's myself and Greg Dudek. And we do a whole bunch of things that overlap with you, so we always follow your research. And sadly today I can only talk about one sort of sub-theme, which is about learning, especially reinforcement learning and robot behaviors. And so I'm skipping most of the computer vision and actually a lot of the field robotics and other things, just to have a focused talk. So Annie gave me a nice preview for this. So here's Barbados. This is the Caribbean Ocean. This is a drone flying just off the coast of Whole Town, Barbados. And so this is where we left Annie stranded in the ocean. This is a coral reef, sort of like a near-shore coral. So there's sand and different species of coral heads that forms a very interesting experimental setup. When the drone starts ascending, you can see that there's a buoy here and some grad students active scuba diving under the water with robot devices. So that's the kind of scenario that we operate in. We're interested in gathering, field relevant information like how are the corals doing? This coral reef is dying, like many coral reefs around the world. There's a coral replanting effort at this spot, so we can help with robots monitor. This is what's happening underwater. This is our robot that I'll show in several of my demos. It's called Aqua. So it has 6 flippers. It propels itself by kicking like you would kick your feet in the pool, more or less. It has camera sensors mainly which guide it. This is currently doing imitation learning-based obstacle avoidance and coral detection. So we've been doing that for several years. My own big focus with Aqua for a while was trying to get it to swim in a more agile fashion. So it was great to see this morning you people are studying birds and all kind of quadrupeds, all kind of agile motion. So I thought it would be interesting that instead of top-down views, which is what many ocean vehicles, boats and glider type submarines can capture, this looks like a very agile fish-style robot, right? So I was interested in could we do a 360 view of the underside of coral reefs and get all the different viewpoints. And that is one of the main entry points that led me. I was mainly a computer vision researcher, and then it led me to thinking about how to control robots like this that are complicated and hard to model and where these kind of behaviors are hard. This is not, I'd like it to be much more agile than this and get all kinds of different views. This is one of the best sort of non-standard viewpoints of a coral reef that we can get with this robot right now. So just to kind of connect up with some of the physics modeling and basic ideas, many people here might know how to model quadrotors and all kinds of different vehicles. We spent a lot of time characterizing the analytical dynamics of a swimming robot with flippers. It's quite interesting because if you take sort of the first order statics force analysis, when you kick a flipper, in still water, if you don't think about how the water moves, you create force upwards when you kick upwards, you create force downwards when you kick upwards. Most of the actual commands we send to this are symmetric and you generate 0 force. So you only generate forward force by kicking a flipper when you think about the hydrodynamics, and you create a vortex and then you kick off the vortex, and if you color the water you see these pattern of vortices spinning on both sides, and it's the moving vortices that propels you. Right? So if you think about trying to come up with a simple physical model of a kicking robot, it's already not too trivial, right? You can fit some parameters and have a sort of second order polynomial style model. It fits okay, it's never perfect. And especially when you want to get dynamic with the robot and be swimming along and then stick up a flipper as a brake, and how does that interact with the vortices? Our models are terrible. So there's a lot of needs to kind of develop new technologies and tools here to make this robot be more dynamic. Some of the work that I did was just in considering the hierarchical behaviors of the robot. It has various sensors, like an IMU, which is sensing its orientation really quickly, and depth sensor, which is changing and has lots of noise, like if you're in the ocean, the depth sensor is biased by the wave motion. And if you want to swim near a coral reef and maintain your attitude looking at a particular coral head, you could maintain your attitude in a tight control loop and roughly try to maintain your depth around where the coral is. And we made some fun use of a 3D PID controller based around some physical analysis. So one thing you want to do with the robot before it does anything useful is dance with it, right? Just push its limits and see, challenge yourself. So if a fighter pilot can do a barrel roll, can my aqua robot do a barrel roll? And if you can do an inside loop or a loop-de-loop, can we do a nice smooth loop-de-loop with the aqua robot, right? So some of the first work that I did when I got to McGill was just testing the physical dynamical limits of this robot, modeling it, understanding how flippers work, and coming up with motions like this. So we do have a lot more command authority about the aqua robot than we did 5 years ago. You can orient it in a variety of different ways. You can swim cameras first, which is the efficient mode of this robot moving through the water. It cuts through the water with a small profile. We can also move, in Canada we call it snow plow because we plow a lot of snow. That's when you move your top flat surface and you point your flippers downwards, and that's what the other video shows. So the controller, which is doing all of those things, approximately is something I designed, not using learning, just using basic analysis. So we do various field deployments. We go every year to Barbados, and we keep developing the control system for this robot. It's a lot of work. Annie talked about carrying the robot in the water as a snorkeler. Even before you get to the water, there's a lot of bits and pieces to attach it as flippers that you have to screw on each time. You have to ballast it to be neutral in the water. So it's real field robotics work. And doing control design on a real field robot, which is a lot of effort to deploy, is a lot of effort overall. So we just are looking for ways to automate the behaviors and learning to swim and adjusting the swimming when we always add different payloads. Sometimes it's towing something. Sometimes it has a box on top which carries a GPS sensor, and the dynamics always change. And so we'd like automated ways to make this rate swimming happen, right? So this kind of pushed us to learning to swim for this robot, right? So I don't want to design controllers. I don't really want to do a lot of hard thinking about hydrodynamics. I just like the robot to adapt on its own, right? And so we've had some success using model-based reinforcement learning. Model-based reinforcement learning means a way to capture the data which comes from the environment. In this case, we just think about the aqua robot. We swim in some way, maybe with the best controller I designed before, maybe with random action. And the data from the real robot is used to capture a dynamics model, which is learned from data, right? And so that can be, really physically informed, and it can say, I know the hydrodynamics properties, and I need to approximate up to second order, and here's the right features. Or it could just be completely naive and deep learning style, and we've done both. And unfortunately, we always get the best results with the deep learning style thing still, even though we intellectually like the dynamically well-informed model to do better. That's a philosophical debate. We just do some modeling. And then once you have a dynamics model, the kind of key trick here is how to improve the swimming policy, right? So I've seen that when I swam with, Dave's best PID controller, we're not able to balance for some reason, right? Maybe the ballast has changed, maybe the flippers are off-centered. And the model captures that, and so an agent, which is perhaps a deep net or some kind of linear controller, can optimize its policies by trying things on the model, looking at the model's prediction. Now the robot's out of the loop, right? So we're actually very data efficient. For one run of the real robot, if we ran it for a long time, collected a lot of data, we could optimize a whole bunch of policies, perhaps. And it turns out that this is really practical, we found, to run on robots these days. It's a little bit computationally expensive, but in terms of data efficiency on a real robot, we get the robot to swim in almost any way that we want in less than 10 trials. Currently we're trying to do the barrel roll, that kind of corkscrew type maneuver, and we started with a completely tabula rasa, random weight policy. And the learning iteration, here is, we've tried 8 times. This is the 8th time we've tried a policy, and it sort of looks like a corkscrew barrel roll for us, right? So the 7 previous trials, the data from the 7 previous trials are fed into the dynamics model. Each time you gather data on the real robot, you update the dynamics model, and you do a lot of policy optimization. So the next thing you try is more informed and gets more and more like a barrel roll, right? So I think for low-dimensional things like this kind of swimming robot, where you mainly just have a 6-stop pose, we're finding that these kind of techniques are quite possible and promising. Right? When you get to a full-body humanoid, some things start to break down, and computationally, even on this robot, you can see it has a tether because this is actually connected up to Amazon EC2 instances where we have, only one small robot, but 20 giant servers processing the data to do the policy optimization or something. Right? So that's something we've been working on and trying to make these things more efficient. The original model that was running on the video that I showed you was essentially just a slight modification of something called probabilistic inference and learning for control, called PILCO. And the main thing there is the dynamics model is a Gaussian process, which scales poorly as you get more and more data. You know, of course, there's many tricks, but it still scales with the amount of data. And to learn, the more complex behavior you want to learn, the more data you need to describe it. And that's also in a tight policy optimization loop, so sort of complexity builds on top of complexity and leads to really long runtimes. So we've been staring at different variants of this PILCO type algorithm. It's especially interesting that instead of a Gaussian process, people have done PILCO with Bayesian deep neural networks. Not us, but other people invented this general framework. So Bayesian neural network can give you the same uncertainty-aware predictions as a Gaussian process, but it doesn't scale with the, you don't have to keep around the data, right? You could have a large data set, you could train on the large data set, and then at prediction time, you just have the neural network's parameters. So you sort of have a fixed, constant cost predictions. You get some better, big O notation complexities. We first tried deep PILCO, which is the citation here on our robot, and we could never get it to work. It was big O notation better, but real world field deployment, we just had no success. Maybe we coded it wrong. But we've been looking at sort of different variations which work better. And our current favorite model, which is actually open source by our lab and several people use, is, I don't know what to call it. Sometimes internally we call it deep PILCO++. We don't tell Yuri Gall that we call it that. We made a couple of changes. We still use a Bayesian neural network for the dynamics modeling. We also use a Bayesian neural network for the policy. This makes everything very coherent and easy to optimize. And so we're still doing this kind of model-based RL here. We're capturing data, we're training the model, we're optimizing the policy in the model. We have to think carefully about the computations that happen when you try to optimize a policy with respect to a model over and over. And we can make it work on our swimming robot and many other things, almost including humanoid, simulated humanoid. We found that it was important. You have these probabilistic models, and so if you sample from them, you add variance to the computations you're doing. Every time you draw a sample, the gradients you compute are different, and this is one of the main reasons why, for example, deep PILCO as it stands might not converge on a particular set of data. Keeps bouncing around as it samples different spaces in the dynamics prediction. It makes a different update. And there's sort of no guarantee to convergence, and practically it often doesn't converge. If you fix random weights in this kind of Pegasus style, which we use in reinforcement learning many times, you say, I only want one view through this dynamics model, and I want to keep that fixed. So imagine rolling out several different trajectories. They're all valid. They're reasonable samples, and as you do your adjustments, you keep those same random weights fixed. Gives you more of an anchor to compute a consistent estimate. So that's helped. By switching to Bayesian neural networks, in both cases, we have better complexity, and sort of it's easier to code in a deep learning package. And so, that's sort of one first early success we had. So I think that this code base that Juan Gamboa in my lab developed is competitive model-based reinforcement learning for anything you might want to do, I claim. We benchmark it against deep PILCO and various, latent variable models which are popular today, and it's really competitive. You can try it for any task, and the code is very clean and nice. And so this is sort of our favorite way to make our real field robots swim, such as the aqua robot I showed you. When we need to recalibrate it, we run this code internally, right? So this is like our engine for real robot reinforcement learning. The big win is that because you're doing dynamic modeling, it's very useful for optimizing the policy. The model-based RL paradigm is nice. It lets you learn swimming policies, but a side effect is you have a really good dynamics model, which you've learned from data and you've been actively exploring because you've been optimizing your policy. Many different policies have been run, you've gathered different data on the system. And so the cool part about this is now, the wide variety of robotics tasks where you could use the dynamics, intentional planning, or what I'll show you next is adapting to changes, or figuring out how to tow a load, which you have the dynamics properties of. You can start to stick together the dynamics model with these other tasks is what it is. We really care about adapting to changes because my colleague Greg Dudek always invents sensors and loves to glue things on the robot. This year, we added 3 IMUs and a compass, which were epoxied on top of the robot because we didn't have time to make a proper waterproof housing. So the robot went from a metal shell with clean, no drag, to something with big blobs of epoxy and electronics on top of it, and holes through the case. The left-hand side is the clean robot with a swimming policy that can do a corkscrew. The right-hand side is this weird jagged robot with different dynamics, right? You'd like that. When you learned how to swim in a variety of ways with the source robot, it's pretty similar, right? It adds drag, but the flippers still work like flippers. The main shape of the robot is still the same. So we think the optimal swimming for our new, modified robot is similar to the swimming for our original robot, and we're trying to learn what we call an adjustment policy. So pi adjustment is some policy which actually takes the source policy. So I'll take as input a way to swim on the other robot, and then I'll take some data from the new robot, and I'll roll out. And the goal is, this doesn't take 8 trials or 10 trials or but we could just run this all the time. And anytime somebody snaps a flipper, or anytime Annie swims up and we ask her to attach the sensor, the online adjustment could maybe almost in real time be learning to swim, right? So sort of slightly more analytically, we'll think about our data, our view on the system will be trajectories, right? So this is not our swimming robot. This is from a cart pole, right? The device swinging back and forth with a pendulum you're trying to swing up. And the sort of the data view we have on the system is that before you modified it, you were balancing this cart very nicely, right? The pendulum is hanging down. The circle is the hanging down pendulum point. The triangle is the goal. You're balancing the pendulum when you get to the triangle. The black trajectory is what you could do before. You had this thing well calibrated. You swung it up, and you could handle disturbances. You had this awesome balancing controller. The dotted red and greenish line with X's are what would happen if you added a weight onto the pendulum. If you had a balancing controller which was doing physics for a light beam, and you added a weight on the end, and you add that same controller without telling it the dynamics have changed, the forces are all wrong, and the momentum's different, so you won't balance, right? You'll try a motion, and it'll swing away. But that's data, right? That's we call it X bar in the previous slide. So you have the balancing controller, and you have what happens now on the modified physics situation. And so we've been doing sort of model-based RL variance to transfer from that set of knowledge to a balancing controller for the cart with a weight on it. We modify our core dynamics model to make inverse dynamics predictions. What should I do next to follow a trajectory? And we look at the red curve, which is data on the real system, and this is training data for the modified policy. And then we do policy search in an efficient way to attempt to resolve the dynamical differences. Here's what that looks like. Here's the run of a learned balancing controller. This could be IL2R. This happens to be Tilco. Doesn't matter. That's the original system you trained 10 times on. Now we add a weight. You can see there's a weight attached onto the pendulum. It's about half the weight of the pole. That's the second trial. So we did one trial with the weight on and it didn't balance, and the second trial it's more or less balanced, and the third trial, and from then on it can balance. The compute time in between here for our method is about 5 seconds. So one rollout, 5 seconds of compute, run it again, and it balances. So the game is how big of weights could you add to this pendulum and keep transferring from the source policy, right? So if you can catch it, the weight that's on the end of the beam just keeps getting bigger and bigger. This one takes about 2 or 3 trials, and it's a little bit more unstable, but after maybe 4 to 5 trials, again, 5 seconds compute between trials, we stabilize to a nice balancing controller for that much weight, right? And I just love looking at these dynamic robots, so I just have to keep letting it play. And I've told you the story already. You know, the key thing here is that these are all pendulums. So they're all carpool. The optimal trajectory to balance a super heavy pendulum and a really light pendulum, if you have enough motor force, is the same, right? So that this guiding adjustment can be a simple computation instead of a search over all possible trajectories. So when we published the paper, we actually said 5 times the mass is too much and our algorithm fails. And we had only run that for about 10 trials. And so in the video, we actually, we start soon playing the ending credits and saying, we need to show a failure case. It's too heavy. A 5 times heavier mass than the pole is just, a totally different trajectory. And we thought it might not balance. So here come the credits. And then after we had published the paper, or after the paper was under review, we said, well, what if we just let it run like 30 times? And it turns out that you are making gradual progress, and you're gathering more and more data for your adjusted dynamics model. And eventually we can balance 5 times heavier mass as well. That's the heaviest we've tried, because we're starting to almost pull the stool over on this thing. So we like these dynamics models. The deep dynamics model learning framework is very strong, and we pushed it to a whole bunch of different things. We've run robot arms that are carrying masses. When we do dynamics modeling for a higher dimensional system like the 7-DOF arm, we try to decompose the dynamics modeling joint by joint and think about what effect does the dynamics of one joint have on the next joint. That looks a little bit like the recursive Newton-Euler dynamics computations. And so we've kind of framed our deep network in a way that captures the same dependencies that you'd have if you did a Newton-Euler computation over the robot arm. And this looks like, waving the robot arm around to gather random dynamics data. And if you train the dynamics model of the arm when it has no load, if it picks up a fairly heavy jug of marbles, they'll be inaccurate, right? It's the same transfer scenario. So it doesn't know that it has a load in the hand, and then it has to adapt to having these loads. And the question is, by exploiting the dynamics dependencies and by just doing this kind of data-driven deep learning thing, could we quickly adapt to any load that we pick up and perform more accurately? And we found some nice positive results on that thing too. So that's sort of the model-based RL successes that we've had. I think they're very field robotics relevant, and we do deploy them on real robots in all cases. We've also had a thread in our lab which is very fascinated by the newspaper, right, and the stream of AI agents winning at the game of Go and chess and Star Trek. Whichever people in the lab play, so we're extremely focused on. It appears that these large deep RL agents, which are typically model-free and do value prediction on these very, very long horizons, are just so strong, right? I mean, how could we bring that much AI, so that long horizon planning and that amount of complexity to robot tasks, right? But we're still roboticists, so that's somewhat interesting, but I'd really like to see the same level of performance on a robot, a full-body robot arm, or in the real world. We've been staring at, does it already work, right? Does AlphaGo translate into a robot to succeed and we can solve all the problems? And, mostly the answer is no, and then we've, of course, been working on deep RL solutions to make these things work better. So, so this is going to be just like the pure RL sense of the world, where an agent just knows nothing about its environment. We're not even assuming that it's a dynamical system. It could be anything. It could be the game Go. It could be StarCraft. It could be our swimming robot. We're going to just be able to take actions on the environment and observe states and rewards. And so that's sort of like the game that the RL community has been playing for many years, and of course it's exploding in the newspapers and in publications. It's just, you know, the RL is taking over, right? Now, the question is it hype? Is it, does it work? And what kind of findings could we have? So does it translate to robots? And the disappointing thing is that in many of those papers, the robots which are evaluated on are, you know, you have to say robots in quotes because they're extremely simplified. The physics are simulated in software simulators, and of course they're far from the real world. But it's interesting to still to stare at what DeepRL can do on these systems. And so here was, you know, the best DeepRL agent to run half cheetah, or, you know, sometime early in 2016. It can stand up, right? And it doesn't fall over, and sometimes it, sorry?
It can't fall over.
It can't fall over. It can flip on its back. So it sometimes flips on its nose, right? Yeah. So it's not very robotic. It's 2D. There's some physics being simulated, but here's ant. It does flip on its back and starts spinning around. So this was about the same, you know, this was around the same time that Go was being solved, and that these big successes were out there, right? So, so we started in this world around that time, and one of the first things we started noticing is that claims on Archive and in the New York Times and things didn't really line up with the code we had in our lab very well. So Peter Henderson was my first master's student at McGill, and he was really excited about DeepRL because of the hype and reasons. He started with some method, which I've anonymized because I want to slightly bash its experimental practices, and it's not personal. It's the same across many methods in this area, so I'm only trying to point out something in this area. So I don't want to say a name of an author or a method. So some code comes out. You take that code, you start running it internally. You try it on a robot arm, on these half-cheetah simulators, you start improving it, and then a New York Times article says, you know, there's been a domain shift in the ability of RL to run robots, and we completely, the same company of course, says we have a new method which completely smashes RL performance, and it's order of magnitude better. You have both code bases as a researcher in this area, and you can run them both, and Peter found they were about equal in his performance. And in fact, he had implementations in our lab which were better than both published results, but method A and method B were about equal, right? And so this was a paper of a group who had published a method and then published another method and shown a learning curve where there was huge statistical significance gap. And so this started us thinking, you know, well, how do we even measure performance in this area? And are these benchmarks okay at all? And what's going on here? And just to keep showing videos, so that was now 2017, and the cheetah was really moving much faster, right? But as a roboticist, you might say, oh my gosh, what are these people doing? You know, this is not how we want our robots to walk on their feet in the lab. But then, you know, maybe as yeah, so maybe we need to be somewhat flexible with our thinking, right? So we started a piece of work at McGill with collaboration with Joël Pinault and Doina Prikat, who pointed out that, you know, a few years before that, there was a very critical analysis of machine learning's empirical side, right? So the data sets that were used, the way that methods were run on the data sets, the claims of statistical significance between methods. And so this long quote basically says, there's many things wrong with machine learning in 2012, which means when people publish papers and claim, you know, difference between results, we can't trust the results. Right? And so we stole their That Matters tag in the title and published a paper called DeepRL That Matters. So we just wanted to say, let's stare at these experiments and say, how can the same authors outperform their own method, and then our reproductions of their codes has completely different ordering, right? Like what is affecting the learning outcomes of DeepRL, and how could we possibly make some recommendations to make this work better. That seemed like an important starting point before diving into the area ourselves, because if we're not doing correct science empirically, that'll be a bad guide for our research, right? So here's some of the interesting findings we had. Here's 2 learning curves over 5 runs each. So, you set up the half cheetah, you learn from a policy that knows nothing, you improve, there's like millions of time steps. The red curve, almost any paper could show the red curve and the blue curve and say the red method is better than the blue method, and almost every reviewer would believe them. These are both the same method, the exact same code, the exact same environment. The only change between these 2 runs is when you first run Python do learning, the first line in your code says set the random seed. And if the only thing you change is to set the random seed to a different value, you get the red curve or the blue curve. So that's pretty depressing, I thought. We could think a little bit about why does the random seed matter so much for these deep RL tasks. You have a software simulator simulating the physics of the environment. You have a neural network which is being started from random weights, and it either could have random weights which could come close to walking or come far from walking, right? And you're running out time series models, we know sort of from ODEs, right? There's huge variability in the time series behavior of these things. So we had to search to find, over random seeds to find things which were this separate. It's not like any random seed you come up with. But it basically means that the way of doing experiments on these software simulations and software agents are all extremely stochastic and have high variance, right? So you should pay very careful attention to the random seeds. And if 2 methods run on different random seeds, you might not be able to trust their A/B comparison. Here's another comparison of 3 curves. You're worried about variance, and we've run over 5 trials again, and you can now see that the blue curve has, better performance and lower variance. So it looks like maybe just stably this is going to be a dominant method. And it turns out that this is just the 3 implementations which are widely used publicly at that time. You can get them from large GitHubs with many, many stars and forks, right? And so many people are using all 3 of these things and calling it TRPO. Several of them are coded by the same authors. One is a reproduction by a slightly different set of authors, and they get such large differences, right? So we all know that, of course you have to code methods correctly, but just the magnitude of difference in entities which have the same name in this world, right? These are all just named TRPO. You don't say always, or at that time you didn't say, I'm using the GitHub from exactly this place and I've modified these 3 lines of code and here's my SHA key of the last check-in, and you just say TRPO. And so you could compare against the baseline with that much variation if you do so. So we found overall that the nuisance factors, the things we didn't want to think about as deep RL researchers, had more influence than the difference between methods, and here's a list of some things which had more impact. And we found that several papers were doing things that just couldn't be done anymore, and we tried to point them out and say, this is not okay. So just to highlight one, for example, people would take the max over many trials. If you just intuitively think about that, here's a method that gives you slightly different performance each trial. It has some variance. And maybe it's a method with really large variance. And so that just means if I run it enough times, I'll explore the high end of that variance curve. And I'm just taking the max over all the runs that I do. So it just means the more times that I run, the better score I'll report. It can't be okay, right? We must take means instead of maxes, obviously. People, really well-cited papers were doing max at that time. The random seed was sometimes optimized over, so that would mean you do hyperparameter optimization of all your, how many nodes you use in your neural network and your learning rate, and the random seed. But the random seed controls how the environment works in this kind of thing. So you could basically be saying, you essentially are able to select the environment's noise, right? So if you're your half cheetah and you have to balance, you could select the random seed that just happens to start you closest to balancing, right? And I didn't really analyze the details, but that's the kind of thing that you could be doing. So we found many, many outcomes in that area, and we reported experimental practices which would remove some of this variance and which would make methods more comparable with one another. For example, showing your hyperparameters and a list of hyperparameters you think people should show, and what should be allowed to tune over. This is somewhat fed into, amongst other efforts, a reproducibility checklist which NeurIPS and ICML and different machine learning conferences use as part of the review process now, mainly championed by Joel Pinot, who is a co-author on this. So it did have impact. The DeepRL community paid attention, and I think people have improved overall. So I think more people run means over many, many trials, and they report their hyperparameters at least, which helps. And I think we can reproduce methods better now after a few years. One problem we've noticed is that, of course, we get the Google Scholar report, who cited this paper, and then we click on the papers, and what's fairly obvious to us is that now you can cite this paper that says there's problems with reproducing DeepRL methods, and we know about it, and we should do things correctly. And then you could either do things correctly or not, right? But the reviewer, seeing your statement that these people have pointed out what to do correctly, will trust you. And so there's like a slight negative trend here that by publishing this paper, we might have given some cover to people doing poor experimental practices. So we're still having an ongoing effort. We can see who cited us, and we can do some machine learning on their papers and so on. And we're thinking of a second version, 5 years later, what fraction of the population actually ran 10 trials, and who tuned their seed and who didn't, right? And it's a little bit more meta to do this kind of work, but there's several people in our group thinking about that. Right? But hopefully it'll get better. I think it is getting better. One thing, being a roboticist working in this DeepRL area and seeing all these crazy things they do in DeepRL, which seem, once we've stared at them, to make no sense, when we're running field trials in our lab and so on, I've been sort of reflecting like, when I put a green background in my lab and set the robot just at this pose because I know something about my method, like how similar is that or how different is that from setting these experiments? Of course, every area has to be careful with experimental practices. But now that we published this paper that people are citing, I feel a little bit more exposed, right? So if we do our usual experimental practices in Barbados, is it still okay? So we're trying to think as carefully about this as possible for many reasons. The next thread that came out of this work, so we were mainly just analyzing other people's DeepRL at that time, right? And what we found is, man, there's a lot of variance here. So when we run the same method, it just doesn't give us reliable performance. And we've got people at McGill who are very strong in reinforcement learning. We've taken their courses. We know the theory. The theory seems extremely solid and promises of convergence and so on, right? They don't say the method should be stochastic and convert to some random value each time. So the question is, what's up with these DeepRL methods, and what elements of them can we analyze that cause this big error? And so one main thing which we saw in the DeepRL That Matters paper and subsequently is I call these methods model-free. And so they don't make a dynamics model prediction, but what they do is they learn with a deep network to predict value. Value means how good is it to be in this state, right? So if there's an optimal trajectory for a robot, then locally the state which has the highest value will be the one which falls along the optimal trajectory. If we can learn that from experience traces, we can optimize good policies. And that's a sort of sub-method of these DeepRL techniques. You can analyze it. You can look at its outcomes, and it's a deep network estimate. So it's supposed to be accurate. If the method's doing well, it'll be accurate. And it's a real meaningful quantity. It's the expected return from now till the end of time, discounted perhaps. And so you can actually run Markov Monte Carlo trials from a state, running your policy millions of times, and you can compute the true value, the empirical, statistically estimated value. The Monte Carlo trial are the dotted curves. The estimate from our deep networks are the line with variance. We found that methods at that time were almost all overestimated. So it wasn't that we saw some underestimates, some over. We just saw overestimates. So that gave us a hint. I somewhat explained what value is already. So it would be deep networks are trying to say how good is it to be in a particular state. They're learning that in a dynamic programming recursive way. They say, well, this state gives me some immediate reward, and then it leads me to a next state. And so I can capture the whole history estimate by doing a dynamic programming decomposition and updating my values. So things that we know we have proofs for is, for example, algorithms like value iteration, which says if I know the full Markov decision process, right, the dynamics of the system or the robot and its rewards, I can exactly compute this and I can guarantee convergence on a discrete Markov decision process. Even if I'm doing learning and gathering rewards and online through an agent, I can prove that things like Q-learning converge on, which is just a way of not knowing the Markov decision process ahead of time, but exploring it and getting data and optimizing your policy. That's also proven to converge since 1989 and empirically converges on discrete problems. One difference for robotics is that all the proofs of convergence of value learning are for these discrete MDPs. And so, like chess, for example, is a discrete MDP. And of course, robotics is more like this. So we're making, continuous actions and having to think about the detail of forces, and we can't keep a table of value estimates, and so we can't even replicate those proofs in our area, right? The kind of theory we have backing up using RL in continuous spaces, states and action spaces, for example, is policy gradient theorem. That tells us that the gradient of a particular value is a good approximation to the gradient that you'd like to compute, and shows you how to compute it. It's the basis of a whole variety of methods that would be appropriate for robotics, right? For the half cheetah and the ant type method. So that's what people are using. That's what people have based their deep RL implementations on, and that's the kind of methods that give us this overestimation bias, right? So that narrows down like what the problem is, and then the interesting insight was the student named Scott Fujimoto. You can see my lab has a lot of gamers in it, like we love StarCraft, and Scott's claim for how he thought of this idea was that he said, when I was a kid, I thought I was the best gamer in the world, and I would be a pro gamer instead of a computer scientist. The reason was because he played his brother only at home, and his brother didn't know how to handle kicks in fighting games. And so he would just destroy his brother every time they played, and he thought, I win 100% of my games, I must be the best gamer ever. It turned out that although he could beat his brother, he could only beat the other parts of his friends who didn't know how to handle kicks either, and some of his friends could block this, or I don't know, I'm not a fighting game expert. Whatever you do to defeat someone who kicks all the time, they could do that. And so his data coming back was, I always succeed with this policy, right? Because he evaluated it on a particular critic, a particular way of evaluating how good is it to kick all the time. And the reality was much different than this, right? So actually we can see this extending in different areas. For example, if I said to my students in the lab, whoever produces the most lines of code this year will get paid the largest stipend, right? Then you can imagine what the Python files will look like that they generate, right? Def, enter, and like one word per line and so on. So once I tell you how I'm going to measure you, you can start to change your behavior to look better on that metric, right? And actually, there's many cases in society where that makes sense. If you say the economy is good when the interest rates are high because the banks usually make high interest rates for growing economy, then a president can just say, raise the interest rates. I want people to think the economy is good, right? So you can only use these metrics if you don't allow gaming the system. And this is like a law in statistics, actually, called Goodhart's law. Measure is, your way of getting feedback on something, and target is what you can optimize with respect to. And if those are the same, you can game the system. You should separate these to make them to make the measure a good critical estimate. So in RL, our critic, our measure of performance, is our value estimate. we're learning this value estimate by training a deep network, and what we're staring at is why is this overestimated, right? There's this loop of you train a deep network, use the deep network to optimize the policy gathers data, trains the deep network again. Sebastian Thrun in early days has a nice result still for discrete action spaces where he said, if you look at the equation up there, which is one of the key equations in reinforcement learning, it says R, which is the reward right now, plus discount factor on the max over your actions of what you do next, and the value of the state you arrive at, is how you're going to update your value of how good it is to be right here. Related comes from the Bellman equation. That's a common update rule. And if you have true action values, that means being at the state and doing a different action, they all have a true value, like the thing you'd really like to estimate. Then you corrupt them with noise, like the noise that comes from a deep network having its weight set to random numbers. So you get a histogram and you want to pick its max, but you imagine the max that you would pick in a histogram corrupted with noise. And as long as the noise has some measure in the positive space, like some of the time you have a positive bias, then this expectation, which you compute with if there's infinitely many actions and you have infinite noise, you just expect to pick a number that's too high. Basically, the max operator, when run on something with noise, as long as some of the noise pushes something higher, it's picking maxes, right? And that's a way that leads to overestimation, right? It's too large, right? Noise leads to too large estimates in this reinforcement learning setup. So that had been proved for the chess playing for discrete MDPs, and at max value. In continuous world, we can't take a max. A robot has continuously many actions. Instead of a max, we take a gradient and optimize a policy to push the policy towards maximum reward. And Scott's paper was the first one to show that when you do RL by taking gradients, but you take a gradient on this policy gradient, which we're taking a gradient over this noisy estimator. So the noisy estimator still has that corrupted values now in a continuous sense instead of a discrete sense. But we managed to prove that gradient descent over a network with that kind of noise in the RL framework also leads to overestimation. More or less, we explained the overestimation. We have a theorem that says it should happen, and it does happen. And we have a fix for it. We are motivated by a fix which has been drawn from in the discrete world, which has been drawn from those Thrun results, which basically says that if it's the noise in your estimator and the max on it that's causing you to be too high, then take two different independent estimators with independent noise if you can get it. And it's less likely that the max you draw will be, the noise will be high in the same places essentially, right? So you get better statistical performance by taking two Q estimates, and there's different variants of that in discrete learning. And so we propose this thing called quick double Q learning, where we have two critics, and we take the minimum over them, right? So the minimum, because we know the gradient is pushing you toward the maximum, so if you just trust one of them, you'll be overestimating. So of the estimates the two things make, I prefer to look at the minimum of the two. And by doing that, you have nicer statistical properties. There's lots more thinking you should do about this particular slide. We thought some more about it, like why is 2 the right number? You could have 10 estimates and take the min over all 10. It turned out it didn't really help us at all between 2 and 10. But I still think there's more to be done here, but we made a first step. And so we make a new RL rule. The new RL rule is the blue curve. We can do the same game where we predict the value of our learning method, and when we Monte Carlo roll out a bunch of times and compute the real value. And you can see that the blue dotted line and the blue learning curve almost fall one on top of the other, whereas the orange dotted line and learning curve have this overestimation bias. So it basically says we can more or less get rid of the overestimation bias. And we formed this into a deep RL method, thinking about how to update the various deep networks as data flows through the system. And the nice part about this is it's very simple. It looks almost like a previous method which we were building off of. It can have very large performance in performance improvements. Again, this is over 10 trials with statistical averaging, and now you should question my results. I hope you do. You can try it yourself because we made the code available, and it's very lightweight, and many people have reproduced this and found also good performance. That's the way that we can claim good performance. The interesting thing is this method is used quite widely now in, reproduced by other authors in deep learning packages that are used in industry. So we have kind of gotten into the game of supporting a deep RL tool for areas that have nothing to do with robotics, which is interesting, but it seems to help. So we've been pretty happy. I'll tell you that I have a whole nother section of the talk plan, but I notice I'm almost out of time. So sadly, you'll have to ask about the rest over lunch or something. My perspective is that robotics is, owning machine learning in many, many ways now, right? Like many things have had domain shifts of improvement. Many people wonder what's the MNIST moment for, I call it, I say, auto advance. Sorry. I say, when will robotics have its go moment? I was so captivated by AlphaGo, outperforming humans, and I still have a feeling that I'm not, when I run my robots with reinforcement learning, it doesn't quite hit in the same way, and I wonder, will that happen very soon, and what are the key steps? And so I think if we stare carefully about how we're running RL on these simulated systems and on our robots and push forward many more interesting benchmarks which are running with careful practices in the community develops. I hope that we'll see a go moment soon, right? That's why I'm still working in this area. Cool.
Thank you. We have time for a few questions. So I would like to kick it off. So let's go. So I have a lot of questions. So let's start from the beginning. The dynamic model that you learned, how robust do you think is that across different flow conditions? You show experimental results in a pool, you show experimental results in Barbados. Based on my few times out, right, the flow conditions are relatively calm in Barbados.
Yeah. Well, I guess one thing is like that robot is pretty poor in terms of sensors, right? So it doesn't sense moving water, and actually it doesn't sense position very well, like maybe with accelerometers, which are so noisy already. So actually our sense for where are we in the water column is pretty bad. We can tell how we're oriented, right, and how deep we are. So I know that I've seen some Barbados experiments where we think we're swimming on a straight line at a fixed depth, and because it's a very high surge day, I can see the robot following the waves, to our view of the world, that's the best the robot can reconstruct, of course, right? And but also the hydrodynamics change a lot when there's turbulence or any of these things. And I would say we're just at the very beginning, so there's lots of more detailed modeling and learning we could do. Sadly. Well, no, there's lots more to do. It's exciting, right? Yeah.
So very early on in the talk, you mentioned that you initially tried to analyze the dynamics of the vortices with the flippers, and then you moved on to either trying to learn analytical models or rather just neural network models. Did you ever try actually some sort of residual learning style approach where you have this physics-based model at the beginning and just kind of try to learn the errors and deviations from that?
Yeah, good question. So this is a few years back, so let me try to. Because actually the project pitch which we wrote a grant for was physically aware dynamics model learning. And so so things that we tried are the dynamics model has a variety of parameters, right? Things like turbulence and flow properties and flipper rigidity and all of these things, which are hard to measure directly, but we sort of know that flipper rigidity contributes a squared term, and this other thing contributes. So we just tried to learn a model which would output parameters for an analytical dynamics model. That worked somewhat. We had run a residual model on top of an optimal control system.